we did, we began with the Kerr spacetime actually. And what we did was to first notice that the Schwarzschild metric, GAB, Schwarzschild, can be written as a Minkowski metric plus some function, plus a null vector field. And this null vector field can be taken to be square root of 2a mod r times either a v, or which is often written as the letter L, not a v, just written as L, or this is if we had used the advanced null coordinate, or we can write it as 2a mod r minus grad AU, either way. And this we often write as 2a mod 1 r times. I'm going to put an n tilde here. The reason is because we used NA to be the null normal to Scri, and a few times we use both Scri and this vector. Therefore, it's just good to distinguish between them. So it's quite remarkable that in fact the Kerr metric can be, the Schwarzschild metric could be written in that form. And the main thing, the next thing I've told you about was about this even more remarkable theorem of Xanthopoulos, namely that if you have got any metric GAB, consider this Xanthopoulos theorem. If we have got GAB is equal to G naught AB plus K KB, where K is null. And last time I left as an algebraic exercise for you to check that if K is null with respect to G naught, it is also null with respect to G. So it doesn't matter which vector you use. And if this, if you like, this perturbation on K, and if first of all the G naught AB satisfies vacuum equation, then GAB satisfies and this tensor, which we just call HAB, just a definition, KKB, this photoproduct null normals, satisfies linearized Einstein's equations on the background metric G naught AB. Then in fact, GAB satisfies the full Einstein's equation. So there are several remarkable facts. Namely, this is given a solution to Einstein's equation. K is a null normal, or is a null vector field. The first remark is that I can define this new metric. This metric has the same signature as G naught AB because K is null. If K was time-like, then this vector field, then this metric would have a different signature, typically space-like. If it was space-like, then this metric would have, if it was a unit time-like vector, unit space-like vector, this metric would have different signature. But with K, you get exactly the same signature. Both of them have the same signature. Furthermore, K is null with respect to both. And Xanthopoulos shows that if in fact this tensor HAB, KB, satisfies the linearized Einstein's equation on this background, then it satisfies the full, then GAB satisfies the full Einstein's equation. So you can add linearized perturbation. It's almost never the case that adding a linearized solution, you'll get a full solution, but that is a miracle of this particular form of metrics. What Kerr and Schild did was, as I began explaining last time, was to consider the special case when G naught was just eta. And so they consider this form of the metric. So this is called the Kirsch Uniform. And precisely because Schwarzschild is of this form, and they're trying to find more general solutions of this form of Einstein's equations. And now there are some very remarkable things happen. First, we already seen that if K is null with respect to eta, it's also null with respect to G, and G has the same signature, minus plus plus plus. And so the Kerr-Schild metric showed several remarkable things. They said, well, let me take now the GAB and impose Einstein's equations. Now, if you impose all 10 Einstein's equations, you get 10 equations on something, which is complicated. So they did it, one can do step by step. So let us just impose that Einstein's equations in the form of the Ricci tensor times K KB equal to 0. This is, and it of course satisfies Einstein's equation. So we're imposing them on G for GAB. So let's ask only the KK component of the Einstein's equation. And then they found that this is the case. So this is completely equivalent to asking that K is geodesic. Equal to something F times. So this equation is just equal to that. And again, the statement is that geodesic with respect to 1, if it is geodesic with a G, it is geodesic with respect to eta and vice versa. Again, the fact that it's null with respect to either just trickles down here. I find this very, very beautiful, very surprising. And therefore they said that, well, let's actually finally parameterize this vector field. And they said that, well, let's suppose that in fact Ka is equal to H times some null vector for LA, and then n tilde A, grad A, n tilde B equal to 0. It is finally parameterized now with respect to the metric G, not with respect to metric G naught, but with respect to metric, the physical metric that we're looking for, the curve metric we're looking for. Now in the case of, let me put it square root of H just because of the factor that here, that we had up here, so that GAB is equal to H times n tilde A, n tilde B. And again, for Schwarzschild, H was equal to 2A more R. Then we can ask more, right? So this is the KK component. Now we can say, well, I got a K, and I ask for I still contract one of the indices with K, but the other one I leave arbitrary. So I just say that now I impose stronger condition. So we assume now that this is the case, this equation is satisfied, and then we impose RAB, KA, BB equal to 0 for all BB. For all vector fields BB, this should be equal to 0. Let's impose that. So we assume now that we already imposed this, and therefore we got this. I can just put it now.
Is this theorem only true when GAB is written as eta AB plus KAB, or for arbitrary G naught AB?
I think it is true for arbitrary G naught AB. I think that there is, I mean, all those things until the last thing are true for arbitrary G naught AB. I say I think because I did this calculation as a graduate student, and I don't completely remember all the details of it. I should look, I can pull up my notes and see what happens. Yeah, I was interested in knowing what happened. This was much before Nixon-Papalou's theorem. I was interested in seeing if in fact we can completely generalize the Kerr-Schild thing. It turned out that the final equation that I'll just tell you becomes complicated, and I couldn't see it geometrically if G is arbitrary. So we impose this condition up here, and then we see that then this condition is just equivalent to say that the Y tensor has some nice property. Last time we saw, or time before, we saw that this Riemann tensor, which has 20 components, can be split into the Ricci part, which is determined by matter, by Einstein's equation. If you're looking for vacuum equations, then of course Ricci part is just 0, therefore the whole Riemann tensor is equal to the Y tensor. And this condition just says that this Y tensor is what is called algebraically spatial. So it has some properties which I'll just now write down, and the property is just that Y tensor has a property that if I put n tilde A, n tilde C, you see this is antisymmetric A and B and antisymmetric in C and D, and symmetric in the interchange, as we saw last time. And therefore, there's only one non-trivial contraction that I can make with the same vector n. It is n tilde a, n tilde b. If I n tilde c. If I had contracted with this wild tensor with n tilde a, n tilde b, of course I'll get 0 because this is antisymmetric, this is symmetric, and so on. The only non-trivial contraction we get are with a and c or b and d, but the two are actually equal to each other because of the symmetry. So that's what we get up here. So this object is then the statement is that this is saying that this is proportional to n tilde b, n tilde b. So this is called algebraic anticipation. Wild tensor. This is very simple and pretty form in terms of spinners, which is where the spin in the class I will write it down. So this is kind of a, if you like, a generalization of the matrix equation, right? If we had a matrix of the eigenvector equation for matrix, the generalization of the, if I got matrix, say in A, B, and I got Ka equal to this proportional to Kb, that will be exactly, like I'm downstairs if you like, is downstairs. So that will be like the matrix eigenvector equation, and this is really the generalization of that. And by the way, we notice that K could be either be n and tilde or L, and therefore Schwarzschild actually satisfies this condition both with respect to n tilde or A or L. So it has two what is called principal null direction. This n tilde is called that principal null direction of the wild tensor. And actually, because this is proportional to n tilde, it means that the principal null direction is repeated. At the moment, let's not worry about the meaning. Those who know. Those who don't know, don't worry about it. It's a repeated principal null direction, and so therefore the Schwarzschild metric has two repeated principal null directions, either the radial outgoing one, or which is L, or the radial incoming one, which is n tilde up here. With a repeated principal null direction. So it's a very geometrical, nice form. So that means that we'll only get solutions of Einstein's equation. If we use his ansatz, we will only get solutions to Einstein's equation, which are rather special. They have some wild tensor of a very special type. And then finally, the question is that we just impose the full equation. So we assume this now. We suppose that the kk component of Ricci tensor is 0. Or n tilde component of the Ricci tensor is 0, and L tilde v component of the Ricci tensor is also 0, and now we're left still with 4 components. Basically, we're saying that contraction of n tilde with respect to n, just one contraction is 0 because it's arbitrary, so that is really 4 equations. We have 10 equations, therefore we're left with the 6 equations, and that is a complicated thing. And so the question is finally the full equation remaining 6. They imply something. I'm going to just write this down. I just want to give you a flavor of what is happening, and we're going to come back to this when we introduce more structure. And the statement is that this is the case when if the vector field n tilde A or Schwarzschild LA up here, if this vector that we got is shear free. Now this is a note. This condition I have not introduced. We're going to introduce it just next lecture. I could take a detour to introduce it, but I think we should just stick with the Kerr metric at the moment today. So it's just some geometrical properties of this null congruence. So these are null rays that are going, null rays. And the thing is that as you go out, if I take a pencil, then that pencil of null rays, the area subtended by them can increase in time. And that is the statement that the null congruence is actually divergence, has some divergence. If the area doesn't increase in time, then the null congruence is not diverging, therefore it's called divergence free. And the other property it can have is that as you go up around, it shears. So this null congruence, so to say, is rotating as we go along up here. there is a very beautiful picture of a shearing null congruence that was drawn by Roger Penrose just outside this room on the other side of the wall, so you don't see it. And that was even in a situation which is a little bit more complicated than the Kerr metric up here called the Robinson-Trautmann solution. And so therefore he has shown there how the Robinson congruence works. You just get a visual impression, don't try to understand in great detail because there is no caption which describes what is happening, how these null rays are going to shearing. What Roger has done there is taking this null congruence which is shearing and projected it on a space-like surface and drawn what happens in the space-like surface. So the geometry can be quite complicated, can be it's very beautiful, but that is what thing is said. The upshot of this is just simply the following, that if in fact G is defined like that, and if we ask that G be also a solution, eta is a Minkowski metric, K is first of all null because we want this to have minus plus 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 signature, then the statement is basically that it is a null congruence which is shear free and the Weyl tensor has some algebraic simplicity, algebraic property, very algebraically spatial. So this is what they found, and this is a very beautiful set of papers that they wrote on this. And then the statement is, as you're saying, that it's a very nice thing to try. If in fact, if this is not flat metric, but any general solution of Einstein's equation. I tried that as a graduate student. I got, I don't know, 30 pages of notes. And up to here, my memory is that it works, but this last form up here, I cannot show it. It's not just shear free, there's messy other terms, and at that time at least I could not simplify it. Again, if anybody wants to try this, you can try this and see if in fact you make further progress in understanding the meaning of this condition in the case when in fact this is not flat metric but a general solution of Einstein's equation. That would be a very nice term paper, extremely nice original term paper, even if you don't completely finish or don't completely understand the meaning of this. If you can get some insight into the remaining equation, that would be nice. But this is a really mathematical kind of term paper. Okay, so this is what is happening. And what Kerr and Schild did was to analyze the space of solutions. First of all, show this and then try to find some specific solutions. Then Kerr took this analysis and in 1963, he used it to find, with a specific goal of finding a generalization of the Schwarzschild metric. Schwarzschild metric at that time was being thought of as being the metric of a point particle, and he was looking at trying to put angular momentum in the Schwarzschild metric. Now we know it's a black hole. Even then people knew it is a black hole, but they were not so careful, if you like, about the fact that it's really a space-like singularity, not a time-like singularity, so you can't really think of it as a point particle in the usual heuristic sense of the word. But he was trying to put angular momentum to the Schwarzschild metric. And then he found this specific solution, which is now the celebrated Kerr solution. Of course, when he found it, he did not know, nobody knew that this solution, its global properties were quickly analyzed, particularly by Roger Penrose, and then as saying Brandon Carter and Roy Kerr himself, in the subsequent years. And they found that there are fascinating physical properties, and that's what we're going to do today to understand those physical properties of this solution up here. Good. So what is this? What are these various functions? So for the Kerr metric then, we got GAB is equal to Minkowski metric plus H times n tilde A, n tilde B. And n tilde is a null vector, which you can take to be just, we'll write down what it is in 1 second. And this is Minkowski metric. Okay? So therefore I can write down now the Kerr metric in this form. And to my knowledge at least, this is the best way to understand the global structure, the singularity structure of the Kerr metric. So this is Minkowski metric. So we have x, y, z, and now I'm going to call capital T as coordinates. I did the same thing for Schwarzschild metric when we did yesterday. The reason is because I would like to use little t to be the Schwarzschild time coordinate, and little t here also to be the so-called Boyer Lindquist coordinate, which we'll introduce in a minute. So I got this metric x, y, z, and t. These are just Cartesian coordinates. And then I had to write down what is h and what is n in terms of this x, y, z, t. So I just have Minkowski space, boring old space-time, and on which I'm defining just two things, a function and a null vector field. The vector field is null with respect to Minkowski metric, as we saw, therefore it is also null with respect to the metric I'm trying to define. And so the H up here is a little bit more complicated than in Schwarzschild. It has two parameters. So in Schwarzschild, it was just 2m over r, now it is 2m r cubed divided by r to the 4 plus a squared z squared. And this new parameter a, so m and a are parameters. And of course, you can just keep them as parameters and then work out what they mean and so on. And at the end of the day, we'll find that this little a is in fact the angular momentum per unit mass, or it is called the spin parameter. Angular momentum absolute value divided by mass, it's called the spin parameter, and therefore it is bigger than 0, or bigger than or equal to 0, and it is equal to 0 if Schwarzschild. And we'll see this explicitly. I just write it down. I mean, it's obvious. If a is equal to 0, I just get 2 over r, get back to the Schwarzschild thing that I have. So that's the first, and this z, just this z, Minkowski z. But of course, in Schwarzschild space-time, r was also the Minkowski r. In Schwarzschild space-time, little r squared in this ansatz was also just x squared plus y squared plus z squared. That is not the case anymore. So little r is a function on the Minkowski space-time, but it's a little more complicated, and it's a root of the equation minus r squared, r to the 4 minus r squared. Let me call it x squared plus y squared plus z squared. And this is the Minkowskian radial coordinate. So from now on, I will just write it as r naught squared minus a squared minus a squared c squared. What is it? So r, this I want to emphasize that this is not, r is not equal to, so r naught is a Minkowski radial coordinate. And so in general, this big R is not equal to little r. But if in fact a were equal to 0, then this term will go away, this term will go away, and therefore I just get r to the 4 minus r squared times x squared plus y squared plus z squared is equal to 0. So in that limit, it is 2. In the Schwarzschild limit, a equal to 0, then it is 2 that r squared is equal to x squared plus y squared plus z squared, or r squared is equal to r naught squared. In that limit, r squared is just equal to r naught squared. But in general, in Kerr-Schild metric, r is a rather messy function up here. But we see here, this looks like a horrible thing, but luckily there's r to the 4th, r squared, and no r dependence here. And therefore we can just treat it as a quadratic equation for r squared and we solve it. And so we're going to get r squared is equal to 2b upon r to 2b. So the usual quadratic equation up here. And then the solutions of this quadratic equation are just 2r squared is equal to r naught squared. This thing, r naught squared b, plus or minus b squared, which is r naught squared, minus a squared, plus 4 times this, and if I get here, plus minus 4 times this, therefore I get a minus 4 times a squared, b squared. So the statement is that we don't want the negative root up here because we want r squared to be positive. If in fact r squared to be positive because we don't want r to be imaginary, so r squared should be positive. Therefore, if I allow for a negative root, then from here it's clear that somewhere it would happen that in fact this term would dominate this term up here, and I will get a it is clear that the total answer is going to be negative if I allow the negative term up here. So the statement is an only positive root because r squared, we want it to be bigger than or equal to 0, just because it's square of a real coordinate. So we only look at this positive root, and therefore the Kerr r is given by this particular formula, where r naught we know in our coordinates, and A we know. So it's known explicitly. It's not it takes the square root, but that's life. And then what is n tilde? So now n tilde, the null vector field, is also more complicated than in Schwarzschild. In Schwarzschild it was just retarded, Minkowski retarded vector, grad U or grad V. These are the retarded vectors. Now it is more complicated. So I get here n tilde A is equal to dt plus 1 upon r squared plus a squared times r times x dx plus y dy minus a x dy minus y dx plus z upon r times dz. As a side remark, let me just mention that if I was interested instead, there's another solution, just like in Schwarzschild case, where you got either L or N, so N tilde or L, and similarly, I also have LA. Curve metric can also be written like this plus eta AB plus some h prime or h tilde times LAB, and then L up here is just given is given by almost the same formula, except that here I get minus sign, and here I get minus sign. Okay. Otherwise, it is the same. So one of the exercises you should do is not very profound, but you should do it for sure. That you show that n tilde A, n tilde B times eta AB is 0. Because the whole idea was that this vector field should be null, so I'll ask you to check that this vector field is indeed null in Minkowski space. And this vector field is more complicated. In here we just had n tilde was just grad of U, so we could just, sorry. Yeah, so we could just, I think I got them mixed up here, so I'm very sorry. This was this was so n was just put in grad of V, and that's what we're generalizing here. And as I told you last time, that we're generalizing grad of V because that coordinate system in Schwarzschild includes the singularity, the black hole singularity, as opposed to the white hole singularity. So n tilde becomes like that. Alright. Now, this is the form of the metric, right? That the metric is Minkowski metric minus dx squared plus dy squared plus dz squared, sorry, dx squared plus dy squared plus dz squared minus dt squared plus h times n tilde b, which is given up here. So let us see where is the metric singular, where is the singularity. See, much simpler. We don't have any problem, near horizon or something. We don't even know where the horizon is up here. And we look at this and say, well, what about this quantity up here? Well, h will have a problem if in fact both r is equal to 0 and z equal to 0, right? Because this is, they're both positive quantities, so both will have to be 0. And here we'll have a problem if in fact r is equal to 0, because otherwise if a is not equal to 0, and if r is equal to 0, then I've got a problem. Let's just focus on a not equal to 0, because we've already done the Schwarzschild case in detail. So r equal to 0 would be a problem, and from there we see that the problem would be when r is equal to 0 as well as a squared plus z squared equal to 0. So let's focus on what happens at r equal to 0. What is the nature of r is equal to 0 up here? Singularity. So this is the only place where there will be singularity. I mean, in the metric as that I have written up here. So if r equal to 0, and even if z is not equal to 0, this is perfectly regular. But then here I find that there is a problem here, namely r equal to 0 up here. So there's a problem. This is actually a potential singularity. The metric is regular everywhere. Already for Schwarzschild, you see that this is interesting, because in Schwarzschild we see immediately here that these in Eddington-Finkelstein coordinates, which are the ones that we're using, v r theta phi or u r theta phi, in these coordinates we see here explicitly that the singularity is only at r equal to 0. Horizon, you don't even see any problem, and you don't even notice that there is anything funny at r equal to 2m in the Schwarzschild metric. And similarly here, the only problem is at r equal to 0. So the question is, well, what happens here when r is equal to 0? Because r is this complicated function, our coordinates are x, y, z, t. So what happens here? Well, if r is equal to 0, then I have to solve this equation that r squared minus a squared plus square root of this is equal to 0. So this is simple algebra, and you do it. And let's suppose first r naught squared is bigger than or equal to a squared, and solve this explicitly. If it is r naught squared minus a squared is actually positive, this is a positive term, this is a positive term. If r is equal to 0, then sum of two positive terms is 0, means that both terms should be equal to 0. So for this, the statement is that r is equal to 0. This implies that r naught squared minus a squared is equal to 0. And these are all elementary algebra, but they teach us profound things in a minute. So plus r naught squared minus a squared squared minus 4a squared z squared equal to 0. Both these terms should be 0. But already r naught squared minus a squared is equal to 0, so this goes away. So it says that is to say, this implies that r equal to 0 and z equal to 0. So the singularity is only in this equatorial plane, namely z equal to 0, not arbitrary values of x and y, but z equal to 0. But arbitrary values of x and y subject to r naught squared minus a squared is equal to 0. So therefore I got this plane in Minkowski space. I forget about time in Minkowski space. I just look at a fixed time. I just look at x, y, z coordinates. And then I got a fixed t. And then I look at x, y, z coordinates. And this is the x, y plane. This is z axis up here. So this is the z axis. And so what do I find? I find that in fact I got a circle. Okay. I got a circle up here, which is r not equal to a. And this is z equal to 0. So what we are saying is that there is a singularity indeed, but that singularity is now a ring singularity. In Schwarzschild, a is equal to 0, so r naught is just here. So in Schwarzschild, the only point where there is a problem with respect to the Kerr-Schild chart, x, y, z, t, is where r is equal to 0. So in Schwarzschild, we saw that we got this picture. This is Schwarzschild. We got this picture up here. Remember, this is r equal to 0. And this chart that we are considering now, which is V adapted to V, this chart is covering this region of Schwarzschild space-time. So we got the horizon as a r equal to 2m, but nothing happens, and the only singularity is at r equal to 0. And this is r equal to 0 is a point in the Kerr-Schild diagram for each value of t. So we just get what is running up here is just coordinate t, and it's a singular point. And there is so at any instant of time, it's a point singularity. But at any value of t, it's not time distance for any value of t, is a point singularity. Or if you like, it's a world line. Whereas here, it is actually for every fixed t, it is a ring. Right? It is not a sphere, it's really a ring up here. And that ring, of course, is chosen by the fact that ultimately we're going to have a rotational symmetry along z-axis, and that is what is z is always preferred, as you can see all over here. That is because the rotation is going to be along z-axis, and that is the thing that we have up here. So the statement is that this r equal to a, this is the singularity, a potential singularity. Everywhere else we're fine. So if there was no problem here, then in fact we will be completely done. I should emphasize here already that if in fact not yet. Okay. So this is a singularity. So the question is whether this is a true singularity, and then one can actually calculate curvature. And the curvature does belong at r equal to 0 and z equal to 0. As r not equal to 0 and z equal to 0 in the chart that we are using, that is where little r, this function, also vanishes, and that is when we have singularity. This becomes singular as well as this becomes singular because of the metric appeal. To begin with, you might think that, wait a minute, but this probably doesn't become singular because I'm already on the z equal to 0 plane, therefore this term is already absent. No, but what we have to do is, of course, take various limits. So this algebraic, you just have to use L'Hopital rule once or twice, or maybe just once, or maybe you don't even have to use L'Hopital rule, depending on how you approach. So the statement is that if I were to approach a point up here from above or from below, you will find that in fact the metric here is not smooth. It is not even C1, and that therefore you've got a singularity. So again, I leave it as an exercise to check that GAV, the metric that we have written down, is not smooth. Now, it's not even C1 at r is equal to 0, which is the same as r not equal to a at 0 and r not equal to 0 and z equal to 0. So it really is a true singularity, it's a ring singularity. A little bit more.
R not equal to 0 to a.
To r equal to 0, which is the same as r naught goes to a. Thank you. Thank you so much. It was a, and then I thank you very much. R naught goes to a, not 0. That's why it's a singularity. So check that, and you can also check that if on the other hand, from inside, I approach one of these points in the inside region, either above, below, that this point is perfectly regular. In fact, from this metric up here, inside, everything is completely regular, but the point that is in, but you cannot really reach this point across the singularity, but you can reach this point either from above or below, and this region is regular. Metric smooth. No problem with the metric up here. And so check that the metric is along these yellow directions, which are approaching z equal to 0 plane for r naught strictly less than a. So the nature of the singularity now has changed. It is a ring singularity. Now we can now ask, okay, but is this a black hole? Right? This is a question that we have asked in Schwarzschild. And in the last week we saw explicitly what a black hole is. What do I have to do to check something is a black hole? Well, we have to first of all take that space-time, conformally complete it, and then see if in fact that in that conformal completion, we got the null boundary is chi plus, look at the past of this chi plus. If it is contained in a globally hyperbolic region, then in fact is it all of space-time or is something missing? If something is missing, then that is a black hole. So we do the same thing up here. Now in Schwarzschild, we did it by looking at the coordinates, for example, for scribe, we use a coordinate u sky plus, we use a coordinate u r theta phi to get sky plus. Sky minus was v r theta phi. What we have done up here is adapted to sky minus because we wanted to include the future singularity, and so in this region, sky minus is going to be included up here. But sky plus is not included because this corresponds to v is equal to infinity, and v is equal to infinity is not included in our chart. So to include v equal to infinity, we have to use the u coordinate, this patch up here. So this patch up was really the VR theta phi, and this chart. And this chart up here is u r theta phi, And this will contain this metric as well. As Emmanuel asked last time, where we could just use U and V and completely forget about R, we can do that, but then the confounding factor is not easily expressible in Schwarzschild, because with U and V, what you get is really, if you subtract them and so on, you get it simply is R star, and R star is a more complicated coordinate. Of course, there's nothing problematic, but it's just that things are not true by inspection. You just have to do a little bit of calculations. So we'll do the same thing as we did in Schwarzschild today. Today we'll do the same thing as we did in Schwarzschild last week. Namely that we just did right now to understand the singularity, we use VR theta phi chart, or we use this n tilde. So this n tilde is what corresponds to VR theta phi, where V is just given by, in this coordinate system, V is just given by T plus R. T plus R not up here. So that is a chart that we're using up here. And now what I can do is to use the chart which is different chart, which will be given by U R not T plus phi. And then see what happens. Everything is really completely similar. You're again going to get something on the other side, and then we can draw the Penrose diagrams. So for this, we can just stare at these equations first. Namely, the only element is the Minkowski space, and the only new element is a scalar function and a null vector. And so the scalar function here is here, and the null vector is here. So what we see here is that the scalar function really is like Schwarzschild. H, we can see here, H is exactly like in Schwarzschild. Then maybe I can take here 2a more R outside, and then I get R squared upon, then I'm 2a more R is taking outside, so I have to multiply by R. So I get R to the 4 up here, and I divide by R to the 4, so I get here plus a squared, c squared up R to the 4. And so we see that this quantity for large R, this really goes like 2a more R plus terms of the order of 1 upon R squared. So to the leading order you get Minkowski space, to the sub-leading order you get Schwarzschild space-time, and angular momentum shows up as 1 upon R squared corrections. And the same thing is true with n tilde. It's a little bit more complicated to check that, but anyway, it's a simple algebra. There's nothing deep about it. You just have to do it, and you find that in fact indeed it is the case that for n tilde, it's also true that we get n tilde to be equal to n tilde a Schwarzschild times 1 plus terms of order of 1 upon R squared. So again, angular momentum appears, a parameter appears here. So in fact, we really, to 1 upon R order, we just have Schwarzschild metric. It's only to 1 upon R square order that you will get some other metric. Now when we did confoundable completion, we saw that for Schwarzschild metric, we saw we see up here that that omega we chose to be equal to 1 upon R, and we found that the confoundably completed metric was given by minus 1 minus 2m omega du squared plus du omega plus little d omega squared. This is the angular part, and this is the part up here. So we see this to be the Minkowski metric, which is minus du squared plus twice du omega plus d omega squared. Sorry, there is the omega squared factor that was missing up here. So this is just the Minkowski metric. If I had a completion of the Minkowski metric, dxa dxp. So the confoundably completed Minkowski metric, plus we get the term which is this term up here, m appears just here, and that term is given by plus 2m omega cube times du square. So in fact, the correction that is appearing to the mean, if I had just flat space and if I had conformally completed it, I would get this metric. If I Schwarzschild, I get a correction, and that correction at null infinity appears at the order omega cube, rather high order up here. And now what we see is that the correction due to the angular momentum is going to appear in an even higher order to the order omega to the fourth. Therefore, the statement is that this Kerr metric is clearly clearly admits a conformal completion with a conformal factor 1 upon r, and I get the flat metric plus omega cube corrections which come from mass plus omega to the fourth corrections of terms of the order of omega 4 which come from angular momentum. So I'm just going to get the same expansion in the Kerr metric, and therefore the Kerr metric is again asymptotically flat. There is no problem. So for Kerr, we're going to get ds hat squared is equal to the Minkowski completion metric ds naught hat squared. This is conformally completed Minkowski metric. Plus terms of 2m omega cube du squared plus terms of the order of omega to the fourth, and then incorporate angular momentum. I could write down the explicit term, but there's nothing at this stage that we can read off from those explicit terms than the fact that they're higher order. And therefore this implies immediately that Kerr metric, the conformal completion, is asymptotically conformal completion to be such that shows it to be asymptotically Minkowskian. And so that's very good. This is asymptotically Minkowskian. And therefore we can ask about black hole structure, and we can just do what we did in Schwarzschild space-time to understand if in fact there is a black hole structure. So again, we start from the asymptotic region up here. I've not yet explained to you exactly what the asymptotic region is, but let me just tell you more heuristically what it is, and then we're going to define it much more precisely. So you again start with the asymptotic region, and the statement is that there is going to be a horizon, and you can complete it. You can ascribe plus, you can ascribe minus, you can do conformal completion. This you can get by using u, the retarded u coordinate. So u is running up here, and this you get by using VR theta phi. And then what we've seen is that in fact I had to explain to you what this, I am drawing this. We do find that in fact path of null infinity doesn't extend to all the way to r equal to 0, but it extends to r is equal to some quantity called r plus. I'm just stating you these facts. You can do it more explicitly, or we can follow what I'm going to do in this next part of the talk, the next part of this lecture. So you don't go here r equal to 2m. This 2m is, if you like, is corrected by the angular momentum term, right? Because this is going to be Schwarzschild, so therefore there's an angular momentum term. The angular momentum term becomes negligible at infinity, but of course inside space-time, angular momentum term and mass term are on the same footing, and other things are all on the same footing. Okay, and then I can also go to the other side. I get r equal to r plus, and therefore the statement is that in fact we got the region 1 up here, region 2 up here, region 3 up here. This also asymptotically flat, so I can ascribe minus here, ascribe plus here. I can do this, and then the statement is that but r is equal to r plus, which is bigger than 0 up here, r equal to r plus bigger than 0 here, but the space-time has only problem at r equal to 0, therefore r equal to 0 is somewhere inside, therefore the statement is that r plus is strictly bigger than 0, And this implies that I was going to say if mass is, unless we're in the Minkowski space, but I mean we're not in the, let me not just write down, right? I mean this is really a black hole, so either the mass or the angular momentum are non-zero. So if R plus is bigger than 0, the statement is that, so that implies that the past stuff square plus is not all of space-time. Therefore, they actually indeed a black hole in the space-time. Now we still have to understand the global structure of the space-time. I just told you that there's a black hole because we just work out what the past is, and then and I can just write down the formula for R plus. So R plus turns out to be where R plus is just given by m plus square root of plus m squared minus s squared. So if a equal to 0, I just get R equal to 2m, but now it is shrunk a little bit. It's a little bit less than 2m. It's m plus m squared minus a squared. So now we have to understand I have to tell you where this R plus came from, where the singularity is, where is R equal to 0 in this diagram, and so on. And that's what we're now going to do. So let me summarize and pause for questions. What was shown physically, the key point is that the singularities structure of Kerr space-time is quite different from that in the Schwarzschild space-time. It really is like a ring, and instead of having a point at any given instant of time or value of time coordinate, it is actually a ring at any given time at any given point. There is no problem outside the ring. There is also no problem inside the ring, and you can reach the problem. So this is the z equal to 0. This is the ring up here, and I can reach these points inside without any problem from x and y, from z bigger than 0, other values of x and y. I can reach these points without any problem. I'll get a smooth metric, so I can go through the singularity if you like. But the singularity itself on R naught equal to a, z equal to 0, actually this curvature singularity. So if I approach exactly at R naught equal to a and z equal to 0, I'll find that metric is really singular and I cannot continue. Now to arrive at this, we saw some very nice, it's both kind of semi-historical and also I think it brings out the structure very well. The global structure is often clearest in this Kerr-Schild coordinates rather than Schwarzschild coordinate, and the reason is simply that in the Kerr-Schild coordinates we're just using coordinates x, y, z, t. There's as Minkowski coordinates, and then the structure is much easier. But now, for many calculations, the Kerr-Schild coordinates are not so convenient because, for example, it is not obvious what the symmetries of this space-time are. If in fact we have a symmetry which is, it's more clear that since z appears all over the place, it's not going to be, the symmetries are not going to be the symmetries of Schwarzschild metric. I'm not going to get spherically symmetric space-time. So what are the symmetries, etc. So for that, symmetries in the Schwarzschild case were also manifest if we went to not Kerr-Schild coordinates, but to the Schwarzschild-like coordinates, Schwarzschild coordinates. So here, the Schwarzschild-like coordinates are Boyer Lindquist coordinates. So now we come to the sixth and last part of this stationary part, which is the Boyer Lindquist. Actually, I should say just say physical properties, geometric integers. Interplay Kerr space-time. So the Kerr-Schild coordinates have taught us that yes, indeed, it is a black hole. And for a not equal to 0, it is not Schwarzschild black hole. And it told us where the what the singularity structure is. But to get a more physical grasp of what is going on, it's easiest to do these other coordinates, which are called Boyer Lindquist coordinates. I want to emphasize that we could do everything in the Kerr-Schild coordinates. There's no problem. There's no problem principle. It's just that things are not as transparent, and also I think you should understand this Boyer Lindquist coordinate, because most of the literature uses Boyer Lindquist coordinates. So these are so the first thing is Schwarzschild coordinates. And these were introduced a bit later by Boyer, Robert Boyer, and Lindquist. And they were the paper was submitted in July of 1966 and appeared in JMP in 1967. So it took a while after Kerr's solution was discovered. Kerr's solution was discovered in 1963. Now here is another kind of small, very sad, dramatic story associated with the Kerr metric. I told you already a sad, dramatic story which had to do with Xanthopoulos, and this is the second one. Robert Boyer was actually a resident of Pennsylvania. He had completed his PhD, and he had worked a little bit in Mexico and had come back to the United States. And at that time, Roy Kerr was in Texas, and I believe that at least when he discovered the solution, he was in Texas. He left Texas sometime, but I don't remember exactly when. And there, Alfred Schild had a relativity center, and it was the largest relativity center in the world. And so Boyer went there to give a seminar on this day. The paper was submitted to the journal in July of 1967, and he went to Texas in August of 1967 to give the seminar. And as he was walking after the seminar, this crazy person in Texas, you might have heard about it, might not have, got up to the university tower, which was very high, and he had a sharp rifle, and he started shooting people. There are many fatalities, I forget now, maybe 20 something, maybe, I don't remember the number. But one of them was Robert Boyer. He just come to the University of Austin campus to give a seminar, right? I mean, and then he was shot, and he died. And so the paper is actually published posthumously. I mean, these are really tragic things that, I mean, it's not that it changes anything that they did, but it's still sort of, to me, it's important to know these things. That's why I'm telling you both these tragedies about Xanthopoulos and about Robert Boyle. And he actually had lined up a job in Manchester, and so he was going to, after leaving Austin, he was just going to, his family had already moved there, he was about to move there, and when this happened up here. So the paper does say explicitly that but by the time it appeared in 67, he had passed away, and the paper says that explicitly. So, the Boyer Lindquist coordinates, where I got R, T, I write little t because this little t is like the Schwarzschild t. It again goes back at the horizons. It's not globally well defined like the capital T in the Kerr-Schild coordinates. R, T, and theta phi, as in Schwarzschild. These are the coordinates, Boyer Lindquist coordinates here. Now, I could write down the relation between the Boyer Lindquist and the Kerr-Schild. In the Schwarzschild case, it was very simple. R was the same, and T, I wrote down last time the relation between little t and the capital T, and so on. It was very simple. Here it is a little bit more complicated. The relation between the phi coordinate that I will construct out of the Minkowski metric, and this phi coordinate is somewhat different, and T coordinate is also a little bit more complicated. So I don't want to do the algebra, but anybody who wants to do the algebra can look at this Carter article, parallel Carter article, in which these coordinate transformations are written down explicitly. The Carter article is, as I told you last time, is on our web page, so you can look at that. So we got RT and theta phi coordinates, and then the metric, the Kerr metric, just looks like dA squared is equal to, it's a little bit long as you see. There's a function of R up here, which I'll write down in a minute, minus A squared sine squared theta upon sigma. So there are two functions that are not explicitly written down, delta and sigma, because they play an important role that we're going to see explicitly. Dt squared minus 2A. Minus 2A sine squared theta So what is delta? Well, delta is the function which is r squared plus 2m, say squared, minus 2mr. So that is just the same as r squared times 1 minus 2m over r plus square of r squared. Therefore, when a goes to 0, that Schwarzschild limit, it just goes to r squared times 1 minus 2m over r. And sigma is another function, so important thing is that this just depends on r, does not depend on anything else. Whereas sigma depends both on r and theta, and that is just r squared plus a squared cos theta, cos squared theta, and in the limit as a goes to 0, just goes to r squared. And therefore, if you like, delta or sigma up here in the Schwarzschild limit just goes like 2 1 minus 2. Okay. So this is the form of the metric up here. And now in the denominator, we got delta and we got sigma. And therefore the metric is singular. Okay, so that's where the metric is singular. And now what we want to understand is which of the singularities is a true singularity, curvature singularity, and which of them is a coordinate singularity, which comes just because of bad coordinates. Now we remember that in Schwarzschild space-time, m equal to 2r was really a bad singularity, was really a coordinate singularity. We could just get rid of it by just using good coordinates, curvature is perfectly fine. Whereas r equal to 0, sigma vanishing, is really a curvature singularity. The same thing is true here, namely that, as one would expect, from Schwarzschild, delta equal to 0 is harmless. Coordinate problem. And this you can check explicitly by, we almost did, right? I mean, we checked that in the case of by going to the Kerr-Schild coordinate, that the Kerr-Schild coordinate we saw that the only problem was at r equal to 0. I should emphasize here that this r is the same as Kerr-Schild r. It is not the Minkowskian r or r naught, but it's the same as Kerr-Schild r. So we saw that as from our Kerr-Schild analysis. That r equal to 0 is the, and z equal to 0. So what is it? Z equal to 0, we have to translate in this coordinates more complicated, but clearly, so I should put it in bracket, that are some other positive values, clearly there is no problem with the singularity at all. Therefore, the statement is that indeed, this is where the horizons are going to be. And sigma equal to 0 on the other hand, sigma equal to 0, as we saw before, when sigma is equal to 0, both these are positive quantities, so r square has to be 0 and cos squared theta equal to 0. But cos squared theta equal to 0 is z equal to 0. You can check it. The coordinates between Minkowski space-time and Boyer Lindquist coordinate, the subtlety is in t and phi. There is no subtlety with respect to theta. So therefore, this really is z equal to 0. So therefore, r sigma equal to 0, this corresponds to the Kerr-Schild coordinate. whatever I got is z equal to 0 and r equal to r naught, r equal to 0 or r naught equal to a. This is really that call, and then this is a really true singularity. But now there is a subtlety, which is what we would first like to talk about, and then we'll end. And the subtlety is that in Minkowski space, in Schwarzschild space-time, the problem was only at r equal to 2m. Like delta equal to 0, this implies r is equal to 2m. So therefore, or if like delta by sigma equal to 0, just says r is equal to 2m. In Schwarzschild space-time, we just get delta equal to 0, r equal to 2m. Just suppose that, sorry, r equal to 0. Let's suppose we're not at r equal to 0, just looking at, look at I can put this one. The horizon came at r equal to 2m because delta vanished there. Now, delta is this more complicated thing. It is actually a quadratic function up here, and therefore we get here delta. Now, Kerr, the roots of delta equal to 0, that implies r equal to r plus or minus, which is equal to what I wrote down here, m plus or minus square root of m squared minus a squared. Again, in the Schwarzschild case, the two roots just give me r equal to 2m. They disappear. There's only one root, but now there are two roots. What this means, and this is what we're going to see next time, but since I have this diagram, let me put it up here, that in fact when I go inside, before I reach r equal to 0, before I reach the singularity, and the singularity is at r equal to 0, as is at r equal to 0, and 2, the equatorial plane up here. So when I decrease r equal to r plus, and then I go inside, before I reach r equal to 0, I reach the second root. Therefore, there is another horizon. So up here, I find that there is another horizon. Here again, delta equal to 0, delta equal to 0. This is r equal to r minus, r equal to r minus. So this is equal to r equal to r minus. And same thing on the other side. We get another horizon, r equal to r minus. So when you cross the first horizon, you don't immediately see the singularity. You actually have a second horizon to pass across. And only when you cross the second horizon that you're going to see the singularity. So something happens which is much more complicated. We're going to spend 10 more minutes on understanding the complete Penrose diagram, just like we understood the complete critical picture. For Schwarzschild space-time, we just have region 1, 2, 3, and 4. And here I got r equal to 0, r equal to 0 space-time stop there. Now, before I reach r equal to 0, I get another horizon. And therefore, life is much more sophisticated, much more complicated. So that's what we're going to see first. And then, we'll conclude the understanding of the global structure of Kerr space-time. And now we'll understand the physical properties of Kerr space-time, just as what we did for Schwarzschild space-time. For example, the symmetries, the killing vectors, what do they define, what physics happens. There are completely novel processes that open up, such as we can extract energy out of the black hole. All those things we'll see next time. Are there any questions? Those who had to go, please go, but anybody who has questions, please stay and ask questions. Yeah.
Is it strictly correct to talk about the topology of singularity, or not really mathematically correct?
Yeah, so I think we can put topology, even as of the ring up, as opposed to line or something.
Can we say topology of singularity in Kerr is S2 cross R, for instance?
No, the topology of singularity in Kerr is just
Is that what was it? So it's a ring?
S1 plus R.
S1 plus R, yes.
Yeah.
That's right.
Yeah, so it's S1 cross R. So it's correct to say, one talks about singularity by just looking at Yeah, I mean, strictly speaking, one should not talk about the topology of the thing, but what one is doing up here is looking at approaching the singularity, namely, in this case, r equal to z, r not equal to a, and z equal to 0. So one is approaching it by, saying r not equal to a plus little epsilon, and z equal to a little bit different, and then you approach it. So for those different values, what is the topology? And that is what we're using. We're doing the same thing for the in the Big Bang singularity case, right? We're saying that, well, is a t equal to constant surface because we're saying that t arbitrarily small, it's a plane or it's a sphere or something, and then what is happening up there? So it's I think one can give meaning to it, but it's not. You have to specify a little bit more to actually be able to give meaning to the topology. But I think the statement is that if in fact r is equal to r naught plus epsilon and z equal to z naught plus or minus epsilon, and you approach, then those curves are all topology S1 cross R.
But we can't really think of it as a submanifold.
No, right? That is really something that's why it's not strictly, again, you can define it by an extension of the idea, but it's really that singularity is excised from the manifold.
Yeah, I was also interested in just the general topological structure of the manifold. Is there
so the topological structure of the whole manifold is, again, I mean, which manifold is the question. So this all is 2 cross R, like in Schwarzschild. Every point is a true sphere, and you've got R and T. So it's S2 cross R, S2 cross R, S2 cross R. And next time we're going to see this is like a global hyperbolic region. And the topology of the Cauchy surface is S2 cross R, like in Schwarzschild.
I see.
Yeah.
I missed a moment the logic of the construction. So you showed that there is this Kerr-Schild construction. So I give you a metric and I tell you if exists this vector k that is has some properties is null and eventually using Xanthopoulos theorem probably, I know that if this k is solution of the linearized equation, then I get a full solution. So what has been used to build this solution?
So the Xanthopoulos, so the question is about the logic of the whole construction for the Kerr-Schild analysis that I presented. There was first Xanthopoulos result, and then there was the Kerr-Schild result. The Xanthopoulos result, if you like, could be really removed from the logic in the sense of we just have Kerr-Schild metric and this is the Kerr solution and we don't lose anything. So Xanthopoulos result is giving you an extra insight into the Kerr-Schild form of the metric. And it is saying that this Kerr-Schild form of the metric has a special property. Namely, the special property is that, in fact, you have got eta AB plus something, and then that is the Kerr-Schild form of the metric. But then that something, if that something satisfies linearized equation, in some sense I can superpose normally we cannot, but in a nonlinear theory I can still superpose sort of a linearized solution to a background solution and get a nonlinear solution. So it's a surprising thing, and that might be useful in practice.
Okay, but even if I stick only to the eta.
Yeah. So let's talk about just the Kerr-Schild part, which is that stick with the background metric eta AB, and then the statement is just that you've got a background metric eta AB and plus KB, and then finally we wrote it as H times some geodesic vector fields and tilde A and tilde B, and then said, well, I mean, then what they have to do, of course, is to solve these equations, right? I told you that this is not geodesic, it should satisfy. If, in other words, you get differential equations, which will say that the algebraic type is something, and then that the congruence is shear free, and so we have to look for solutions.
So if I have those conditions, I have solutions.
Yeah. So those conditions are necessarily sufficient to say that I have a solution. But now we have to pick a specific solution. So there's a whole family of Kerr-Schild solutions, and the great skill that was required in the analysis by Kerr. There is a preceding analysis also by Newman and so on. I mean, there's a lot of history to this. Was to pick out one solution. That would be generalization of the Schwarzschild solution, which might have angular momentum in it. So that is, there's no strict kind of logic to it as to why this solution, why not that solution. You solve the equation, there are many solutions, and then you actually find one that you think is physically most interesting.
I see. So, for example, how much freedom do I have in choosing age? I'm thinking to this just because I'm thinking to, for example, non-singular solution, other things that seems to me just generalization in which somebody, for some physical reason, changes age. But
yeah, so the equations are coupled. They're coupled nonlinear equations between N and between H. So
so as soon as I'm able to solve it, I have a new solution.
A new solution, but yeah, sure. So I think that these are actually explicitly written down in the Kerr-Schild papers. If you want, I can put those papers also on the website. So yeah, so there are those explicit solutions, and so therefore, as you say, one might be able to look at them and see if, in fact, the point is that when you're talking about non-singular solutions, you're violating Einstein's equation.
Yes.
And therefore, this whole thing is not very useful, right? Because
it's just saying
so
the generalization of these that is not a solution,
yeah,
but
exactly.
has the same shape essentially.
Good. So therefore, what one would like to do, I mean, what would be, it's a nice idea to do, like generalization of construction that Carlo and Hall had done, would be to perhaps assume that the metric is of Kerr-Schild form and find some metric which is of the Kerr-Schild form and has some global desired properties which might reflect what you think physically might happen when there is a bounce or when there is a singularity is avoided, and then go and see in what region Einstein's equations are violated. So the H is going to differ from Kerr-Schild H somewhere, and is also going to differ, or maybe and is not. I mean, of course, the simplest thing would be not to worry about the Kerr metric, but just look at the Schwarzschild metric, where things are really, really simple. And then the statement is that you could try to do that, try to see if, in fact, again, using V and capital T, X, gives a V and R and theta phi. This is chart. One can just, in short, for Schwarzschild, right, I'm write it in the Kerr-Schild form, and say that when I got H, which is 2m over R, now it is something else, and then I'll just write down a metric and see what the bouncing looks like. And then the question is whether something like loop quantum gravity is providing some natural mechanism with additional terms to Einstein's equations, so that the resulting equation is satisfied by this metric. So it's a good answer.
But do I know from the beginning that if I do something weird on H, this will violate Einstein equation?